So now that we remember some stuff about inverses, we can talk about the derivatives of inverses. And we're going to relate it to the original function because we're talking about an inverse. We have an original function that we know. All right, so first thing to remember is if a, b is on the graph of the original function, the inverse is going to flip it. So this x value becomes the y value, and this y value becomes that x value on the graph of our derivative, or sorry, not derivative, our inverse function. All right, so if we have a point on our function, the opposite point is on the inverse. And then since everything's getting flipped, if we have a slope of AB on the original, when it gets flipped, the slope is going to be B over A on the inverse. All right, so here is kind of a graph of what's happening. So we saw in the inverse video that the reflection over this diagonal line, y equals x. All right, so this is our original graph. Which one is the original graph? This is the original graph here. And our original graph has this tangent line. And our reflected over the diagonal line, that my inverse graph is this graph. It has this tangent line. All right, and you can see whenever we have a tangent line on the original, when it flips, kind of the run here becomes the rise there, and the rise there becomes the run there. So if we know one slope, we can get the other slope there. All right, so just knowing that the slopes of derivatives and inverses are related. All right, this leads us to the inverse function theorem, which is another way to find derivatives of inverse functions. And we know it's just the flip of the thing. So 1 over something gives us the reciprocal. But there's also the weird thing with how the a and the b point are flipping. So what we do is we take 1 over the derivative of the original function, but then we plug the inverse into that. All right, so we'll see with this in an example. It's a little weird, all right, but it's kind of just something you have to memorize about how you can find the derivative of an inverse. All right, so let's do an example. So we're going to find the derivative of this inverse in 2 separate ways. So first, let's do the way that we learned before. The derivative of this inverse function, so this function here. All right, we could do it 2 different ways, but I'll do it using the quotient rule. We do low, right, d high, minus high, d low, all over the bottom squared. This part's going to cancel out, so we're just going to get -2 over x minus 1 squared. And that's a perfectly fine way to do it, and that's actually how you would do it most of the time if you knew exactly what the derivative function was and could find, the inverse function was and could find the inverse. All right, let's see how we would do it using this inverse function theorem. So the first thing we have to do is find the derivative of the original function. Let's separate these out. At the derivative of the original function, we could do using the quotient rule again. So low, d high, minus high, d low, all over the bottom squared. And if I do a bunch of simplifying, I'm subtracting x minus 2. I'm just going to get -2 over x squared. Now the next thing to do using the inverse function theorem is I'm going to take my inverse function, the original inverse function, and plug it in to my derivative function. All right, so that's going to look like this. Oops. That's -2 over, instead of x squared, I'm taking this whole function here and squaring it. I'll just do a little bit of simplifying. And using properties of fractions, you can simplify this composition to here. And then our final answer using the inverse function theorem is that the derivative of our inverse function is 1 over this composition. And again, 1 over something just means you take the reciprocal, so I flip this answer I just got. And you can see that we get the same answer that we got up here. All right, so this one was just kind of the direct way using the quotient rule. This was using the inverse function rule. Again, in practice, if you had this function, you wouldn't do the inverse function rule, but you use the inverse function rule when you don't have enough information. Again, the AP questions are going to make it so you don't have enough information. You have to kind of know this inverse function rule. All right, this is showing how it works. All right, you take the derivative of the original, all right, so that was here. You plug the inverse into that and do a bit of simplifying, and you take the reciprocal, you flip it to get your very final answer. All right, so that was doing it for an entire function. All right, what about an individual point? So if I want to find the derivative at a single point, b, again, it's the reciprocal of the related point from the original. So the original, you take 1 over a, right? A and b are related. But when you're plugging in a into your inverse, that's like you were plugging in a into your original, because that flip happens. So just remember, the derivative of an inverse is a reciprocal, and the fact that the points are flipping. All right, so this is a very common question that you'll see on the AP exam, is they'll kind of give you this information and ask you to find f inverse prime of 2. All right, so we're trying to find the derivative, the slope of the tangent line of the derivative, sorry, not the derivative, the inverse at 2. So we're finding the slope of the tangent line of the inverse at 2. And our little thing that we just had, if we want to find the derivative at 2 of the inverse, it's the reciprocal, so 1 over the derivative of the original, but we have to do the flip. All right, so this is where I have to think about the relationship between the inverse and the original. If I'm plugging 2 into my inverse, that means I'm getting out 2 from my original, which means for my original function, I'm actually plugging in 1. So this is going to be f prime of 1, which is 1 over -2. Your final answer is -1/2. So this is kind of the two things that are happening. The first thing that's happening is when you take the derivative of the inverse, you have a reciprocal. All right, so that's 1 over, so I'm just going to flip kind of whatever answer I get. And the other thing that's happening is the number I plug in here is different than the number I plug in here, because this is the number that's getting plugged into the inverse, which is the number I get out of the original. All right, so the numbers that here are going to be different because one's related to the inverse and the other is related to the original function. All right, so a little complicated, but this is kind of the exact type of question I would expect to be on the AP exam that's relating inverse functions and derivatives.